Hey guys, this is an additional video if you need more help on chair conformations and specifically ranking the stability of chair conformations, which will be probably the finale of what you'll have to do with chairs. It's not a very long section in organic chemistry. So let's go through each of these. For each compound below, draw the most stable chair conformation. So let's do that. Feel free to pause right here if you need more time, but I'll just keep it going and you can see if you get the same answer as me. So I'll draw out my chairs. Let's slant them. I'm going to draw them out in advance. Okay, so I have both chairs. Again, the numbering, you can see my other video on the numbering and why they're different after you do the ring flip. That's the numbering. And here's the numbering on the cyclohexane. Okay, now let's think about where to put these substituents. We have two methyl groups on carbon 1 and carbon 3. They are both wedges, and wedges mean up, so you want them to point up. So carbon 1, we have a CH3 group, and carbon 3, we have a CH3 group, both going up. Okay, we will worry about axial and equatorial positions once we filled in both chairs. So for this one, again, it stays the same. Wedge is up, CH3 group, and wedge is up, CH3 group. Which is the more stable chair conformation? Now, if you watched my previous video, you know that the more equatorial positions, the more stable the chair conformations is. So we have these two chair conformations. We want to look at which one has more equatorial positions. And I would say that this second one that we did the ring flip with is more stable because this is in an equatorial position and this other CH3 group is in an equatorial position, rather than the axial positions that these two are both in. Okay. For this next one, let me do the same thing and draw out both the chair conformations. Okay. Okay. So now we have a little bit of a different scenario. We don't have methyl groups. It looks like we have an isopropyl group on top. So that's isopropyl, and we have a methyl. So carbon 1 is the isopropyl, and that's pointing up. That's a wedge. I'll label that IP. And then on carbon 4, we have a methyl group that's pointing up. Okay. Now on the ring flip, let's do the exact same thing. The isopropyl is still up, and the methyl is still up. Now, what's the difference and how do you determine which one is more stable? We have both of these have one equatorial position, right? We have this in an equatorial position and we have this in an equatorial position. They both have one equatorial position. Then you look at which one is bigger or more electronegative is better. So the isopropyl is bigger in nature than that methyl. So subsequently, this one will be more stable because we have a better group on an equatorial position. Okay. This one we're dealing with tert-butyl groups. Okay, so we have two tert-butyl groups. I'll start labeling this. Let me draw out my chairs. That's not the best chair. It's a little bit better. Okay. Write my numbers again. Again, if you do enough practice problems, those numbers, there's a couple different ways that you can number it. It doesn't have to be one on that top carbon right here. You can kind of switch it around, but that's just how I do it. So on our 1, we have a wedge. That's a tert butyl group. I'll just do that abbreviation, T-BU. And then on carbon 4, we have a dash, which is down on tert butyl. Okay, and then same thing for this ring flip. We have a tert butyl group on 1, that's a wedge, and then a tert butyl group on 4, that's a dash, so that's down. Okay, which one is more stable? Right away, this one is definitely more stable because both tert butyl groups are on equatorial positions on that second one. So that's going to be more stable. Okay, this one. Okay. I'm just going to do 1, 2 on both of these because we only have 2 substituents on carbon 1 and 2. On carbon 1, we have a ethyl. So this is an ethyl pointing up. So a wedge is up. So I'll just write that ethyl, or feel free to draw out 2 carbons. I'm just going to put ET. And then on carbon 2, we have a dash, which is down, and that's just a CH3 group, a methyl group. On our ring flip, that ethyl is still a wedge, right? It doesn't change, and it's going in an equatorial position now, and our methyl is right there. Now, the important thing here is that ethyl group. That ethyl group is bigger than that methyl, so we really want to track that and see how that changes. So that ethyl group was on an axial position, and now it's on an equatorial. So this is going to be the more stable chair because it's on an equatorial. And so is that methyl too. They're both on equatorial on that second chair conformation. Our last one here, that's too slanted. Okay. We have, let me say that's carbon 1 and carbon 2. 1, 2, whoops, 1, 2. Okay, so on carbon 1, we have a methyl group. Feel free to call that Me as well, that also works, but for simplicity, I'm just going to do a CH3 group that's pointing down. It's a dash, which is down. And on C2, carbon 2, we have a wedge that is up. So we have 2 CH3 groups right there. Our second one, we're going to have a dash, which is down on carbon 1, CH3 group, and then a wedge that is up. It's a CH3 group. This first one is definitely going to be more stable, right? Because those both methyl groups are on equatorial positions, so that would be more stable. And that is about it for chair conformations. Obviously, you're going to have chairs which I told you about in my previous video that have a bunch of substituents on there, and you have to really choose which one is going to have more equatorial positions, or is a stronger equatorial substituent. So feel free to watch my previous videos. My next video is going to be on stereoisomers, so stereocenters, chiral centers. So feel free to watch that video as well. I'll see you guys in the next video.